This is recording, and it is great. So let's get started. Last time we have seen the mean value theorem, which states that if f is continuous on AB, differentiable on the open interval AB, then there exists C in the open interval such that f of B minus f of A is equal to f prime of C times B minus A. Okay, and we have seen nice applications. One of the applications that we have seen is bounding functions. Now I've got an example. Show that tan x is strictly bigger than x for x in 0 pi over 2. I did it in one way. So what I did is that I took g of t is equal to tan t minus t, and applied the mean value theorem on the interval 0x. Okay? That's what I did. Now I'll do it another way, which may be easier, which I think is easier. I mean, I realized that after the lecture, I was like, oh, this is not very smart of me to do the other thing. Okay, please let's find a spot, please, as fast as you can. So let g of t be equal, let h of t be equal to tan t. Okay, this is another way of doing it. It's equivalent, really it's equivalent, but you know, that's fine. So let h of t is equal to tan t for t in 0 pi over 2. Okay, we know that h is continuous on 0 pi over 2, right? Because tan t is not defined at pi over 2, and differentiable on the open interval 0 pi over 2. Now notice that x is between 0 and pi over 2. Hence, by applying the mean value theorem to h on the interval 0x, which is contained, this is contained, well, that's fine, on 0x, what do we get? We get that there exists C inside the open interval 0x such that g of x minus g of 0 is equal to g prime c times x minus c. So far so good. I just apply, oh, h, what are h? It's h of x. Is that clear? You agree that x is between 0 and pi over 2. So h is differentiable on the open interval 0x and continuous on 0x. You guys see this or not? X is between 0 and pi over 2. Any questions on this, please ask. Yes?
How did you make
Oh, because well, that's part of it, right? You have to guess what the interval is. But in that case, it's not very hard. What is g of x? What is h of x here? Tan x. Very good. What is h of 0? Tan of 0. Great, so you get something nice, right? Everybody, we get something nice. What's tan of 0? 0. Oh, well, I got tan x on the other side. What's h prime of c? This is secant squared of c times x minus 0. Now, c is between 0 and x. Well, let's write this down in a better way. Okay. Tan x is equal to secant squared c times x. You agree with this or not? Everybody, you agree with this? Now, C belongs to the interval 0x. Let's C belongs to the interval 0x, or 0. C is between 0 and x is less than pi over 2. So secant squared C is strictly bigger than 1. You agree with this? Everybody, you agree with this or not? C is non-zero and is in the first quadrant. You guys see this? So secant squared of C is strictly bigger than 1 because C cannot take the value 0. Oh, okay. So secant squared C is bigger than 1. Now tan x is equal to secant squared C times x. Now x is positive. You agree that x is positive, right? So secant squared C times x is just bigger than 1 times x, since x is positive. So tan x is strictly bigger than x if 0 x pi by 2. Okay? Are we good here? Is that clear? Are we good? Yeah? Yes or no? Oh.
How you got like the open interval 0x again?
I see. So the open interval 0x, I just want g of x to be 10x basically. Okay? So it's yeah. How do you guess it? You just practice. Okay? You apply the function h on the interval 0x or on the interval 1x, or depends. Every time you apply to an interval, you get a different result. Here you have to guess that the interval is 0x. Okay? Most likely, I mean, that's what you'll get. You'll have to apply it on the open interval 0x. Okay? I don't know if we should do one more, but let's do one more. Show that if x is positive, then arctan x is less than x and strictly bigger than x over x squared plus 1. If x is strictly positive, then arctan x is strictly between x and x over x squared plus 1. Great. That looks as a tough problem, like a tough problem. But again, what is the function I want to bound? Arctan of x. You agree? That doesn't look easy, but it's really 3 lines, once we justify. So I'll help you out. Let h of t be equal to arctan t. We're going to apply the mean value theorem to arctan t on what interval? So if h of t is equal arctan t, what is h of x? Arctan x, right? What is h of 0? Arctan of 0. So really your interest is to put this as h of x minus h of 0. Okay? This is what you want. So if you let h of t is equal to arctan t, what is h of x? Arctan x. What is h of 0? 0. So the middle part, arctan x, will be h of x minus h of 0. So h is continuous on 0x. Of course, let x be positive. That's an assumption. And differentiable on 0x. And what is h prime of t? Is 1 over 1 plus t squared. Okay. Let me apply the mean value theorem. Oops. Oh, well, that's from last time. Let's apply the mean value theorem to h on the interval 0x by the MVT on 0x. There exists C inside the open interval 0x such that h of x minus h of 0 is equal to h prime of c times x minus 0. Agree or not? Yes or no? I just copied this statement. H of x minus h of 0 is h prime of c times x minus 0. So far, so good. What is h of x? Arctan of x minus h of 0 is 0, right? Arctan of x minus 0. What is h prime of c? H prime of c is 1 plus c squared times x. You agree with this? Everybody, we agree with this. Great. Now, what can I say about 1 over 1 plus c squared? This is strictly less than 1. You agree with this? You agree? That's clear. So, since x is positive, x is positive, and 1 over 1 plus c squared is a positive quantity and strictly less than 1, then arctan x, which is equal to 1 over 1 plus c squared times x, is strictly less than 1 times x, which is x. Agree or not? We agree? So far, so good. I got one equality. Oh, where's the... It's upstairs? It's down? Where is that? I got this equality. This inequality. Arctan x is strictly less than x. Now the other one. It also follows from this. C is between what and what? 0 and x, right? Okay. Can you read this? Okay. Since C is between 0 and x, what do I have? I have that 1 over 1 plus c squared is bigger than 1 over 1 plus x squared, which is also positive. You agree with this? Everybody, do you agree with this? You agree or not? You agree with this? So C is between 0 and x, so c squared is less than x squared. So c squared plus 1 is less than x squared plus 1. Both of them are positive. You take the reciprocal, you switch the order. Is that good? Okay, so c is between 0 and x, so since x is positive, you have that x over 1 plus c squared, or 1 over 1 plus c squared times x, is bigger than 1 over 1 plus x squared. I multiplied both sides by x. Agree or not? Now, what is the left-hand side? Look at the left-hand side. Look at the right-hand side board and look at the left-hand side of this inequality. Look at the board at the extreme right. And look at 1 over 1 plus c squared times x. What is that? Or look upstairs. What is 1 over 1 plus c squared times x? Arc tan x. So arc tan x. So is bigger than x over x squared plus 1. Okay, so that's a bit tough. But I think the class is strong enough to be able to master this stuff. Yes?
In that inequality, why isn't it greater than 1 over 1 plus x squared times x?
Oh, I should multiply by x. Sorry. I should multiply by x here. Yes, 1. Okay. I multiplied x on both sides. Thank you. Are we good here? It's a bit tough, but the key is to practice. Yes, sir.
Interval 0 to x, so they can apply to mean value theorem.
Exactly. Guys, someone is asking a question. Yes.
So sometimes it may vary depending on the function, so there should be intervals that you can apply to mean value theorem.
Exactly. So what you want is the middle part, or the function that you want to bound technically, to correspond to h of b minus h of x. Okay? There are many ways of doing it, but so you can take, for example, h of x to be arc tan x. Well, you can, but you can do it in the easiest possible way. Okay? Great. The idea now, this question has been asked before, right? So when we did this problem that I erased, people have asked me, do we have to find the bounds on the derivative? Remember, we did that question. So say I have f of 1 is something, and I bound the derivative. How large or how small can f of 4 be? Right? You remember this question? We did this last time. This is the same type of question, but I have to bound the derivative myself. Okay, great. Are we good here? It's not easy, but practice it, okay? I mean, I can give you some more inequalities to show. Okay, you can practice those. Yes?
Please again explain how you think of intervals.
Practice. So the idea is that you want just arc tan of x to be h of x minus h of b minus h of a. Okay? So you want arc tan of x to be equal to h of x to h of b minus h of x. Okay?
That's the mean value term.
Yeah, I mean, to apply the mean value theorem, you need to find the interval a, b. Okay, what's a good thing? So you know that if h of x is arc tan t, okay, then what do you get? H of x is arc tan x, and h of 0 is arc tan of 0, which is 0. Now, say you have ln x. You want to get ln x as h of b minus h of a. What would your interval be? So the last bound would be x, right? Ln x minus what gives you ln x? Minus ln of what gives you ln x? It's ln x minus 1. Minus ln of 1, basically. Okay? That's what you're looking for. So basically, if you want to get, say, ln x, you want to write it as h of b minus h of a. So say here x is greater than 1. So you let h of t be equal to ln t, right? Then h of x is equal to ln x, and h of 1 is equal to ln 1, which is equal to 0. So ln x will be equal to h of x minus h of 1. Okay?
What if you have like sine or something?
So it depends on the interval, right? You can do it sine as sine x minus sine 0, right? Cosine x, you could write it as cosine x minus cosine pi over 2. Okay, if x is bigger than pi over 2, you can apply the mean value theorem there.
So you're always just trying to get the function minus 0.
Minus something that is 0. Minus the function at a point at which it's 0. Yes? Yeah.
So the upper bound of interval, is it important that it has to be where f of x is x.
Where f of x is x?
So, because like for example, here, take your lower boundary is where arctan of x is 0, so you take arctan of 0.
Yeah.
And then your upper boundary, you take arctan x.
Yeah. Because I'm looking for this.
Yeah.
Okay. Great. We'll continue with more examples and application of the mean value theorem. And do more stuff. That's very easier. That's a very, the mean value theorem is one of the most important theorems. Okay. So all of this is very important actually, okay? So please make sure you practice this. Other applications. Let's look at something. Suppose f is differentiable on an open interval AB. It's important here that AB is one interval, okay? It's not everywhere, just one interval on an open interval AB. And suppose that f prime of x is equal to 0 for all x in AB. Then f of x is constant on A. So I have an open interval, AB, on which the derivative is 0. Identity. The claim is that f prime, that f is constant. Let's show this. Proof. Let x1 strictly less than x2 be in the open interval AB. Now f clearly is continuous on x1, x2 and differentiable on x1, x2. Right? You guys see this why? Because x1, x2 or x1 is strictly less than x2 and x1 is bigger, strictly bigger than A, and x2 is strictly smaller than B, right? You see that? This should be obvious. And hence by the MVT there exists C in the open interval x1, x2 such that h of x1, or well, h of x2 minus h of x1, or what am I saying? F of x2 minus f of x1 is equal to f prime of c times x2 minus x1. So far so good. I just applied the mean value theorem here. Now notice something. fx2 minus fx1 is f prime of c times x2 minus x1. Now what is an assumption about f prime? That is 0 on the open interval AB. So what is f prime of c? Everybody, what is f prime of c? 0. Since f prime of x is 0 for all x in AB, then f prime of c is 0, hence f of x2 minus f of x1, which is f prime of c times x2 minus x1 is equal to 0. Great, let's bring the fx1 on the other side. So fx2 is equal to fx1. So no matter what the 2 points are, you get the same value of f. So what can you say about f? Constant. Okay? So f is constant on AB. Okay? It's a bit hard to grasp, but think of it this way. If you have a derivative on an interval that is 0, then f is constant on that interval. Okay? Great. Let's do an example of this, or let's generalize this a bit. Another theorem. Okay. Now suppose that H and G should be T and H are differentiable on AB, and that H prime is equal to G prime of X for all X in E. So you have two functions defined on an open interval, right? Two functions defined on an open interval whose derivatives are equal at every interval, at this interval. What can we say? Then, maybe let's give a nice interpretation of this in terms of physics. What is f prime? What is f prime? F prime is the velocity. Okay? Look at the theorem I just put here. I just hit it. Okay. So what is this saying? So suppose f is differentiable on an open interval. I am walking. Okay? F prime is equal to 0. What does it mean? It means I have no velocity. Am I walking? No. So what can you say about my position? It's constant. Is that clear?
Yes.
Okay, that does that make more sense than this?
Yes.
Okay, now let's look at this. Well, this doesn't make a lot of sense. This I cannot make more sense. I mean, okay, let's see. So if I am here and the chalk is here, okay, and both of us are walking at the same position, at the same velocity, sorry, right? This is what this says. That the velocity of the chalk and my velocity is the same. What can you say about the difference in displacement? It's constant. That's clear, right? So if you start here and I start here and we're both walking at the same velocity, does the distance between us change?
No.
No. This is what this says. So h prime for all x in AB, then h minus g is constant on AB, or there exists K and R such that h of x is equal to g of x plus c. Okay? The proof of that, let f be equal to h minus g, okay, and use the previous theorem. F prime is 0 on the open interval AB. Use the previous theorem. Use the previous result. Okay, this is left as an exercise. Take the difference. The difference is 0 on the open interval AB. Has the 0 derivative on the open interval AB. So f minus g must be constant on the open interval AB. Reset your equations, and that's what you get. Awesome. Great. Let's apply this. Exercises. I mean, the book doesn't have that many, so I'll try to give I think the book has only two or three of them, so I'll leave them for you. But this is also very important to do. So let's see what I can find. Show that. Making those on the spot. Let's see that cos that for all x in 1 minus 1. Cos inverse of x is equal to pi over 2 minus sine inverse of x. Cos of pi over 2 minus sine inverse of x. Yeah, okay. Cos inverse, you know what cos inverse, our cos basically, right? Cos inverse of x is equal to pi over 2 minus sine inverse of x. Okay, now we'll see a small difference of this and the previous result you have seen. We have to take care of one thing, but we will do it very smoothly. Okay, great. That you don't need this. You don't need the derivative business, right? You don't need that. You see why? You don't need that, but let's do it using this mean value theorem thing. So I mean, let's see. Let's plug in cos inverse of root 2 over 2, so pi over 4, you get pi over 4. Let's plug in 1. So sine inverse of 1, what is that? Pi over 2, right? So pi over 2 minus pi over 2 is 0. Cos inverse of 1 is also 0. Let's plug in minus 1. So sine inverse of minus 1, what is that? This is minus pi over 2. So pi over 2 minus pi over 2. Cos inverse of, yeah, that's fine. That looks good. I mean, you can just also take cosines of both sides. Anyways, let's not worry about this. But let's show this using the mean value theorem. So, what do I have to show? Really, I have to show that two functions are equal on so let g of x be equal to cos inverse of x and h of x be equal to pi over 2 minus sine inverse of x. For x, of course, n minus 1, 1. Okay, now G and H are differentiable on minus 1, 1 and continuous on minus 1, 1. That's clear, right? You guys see this. So far, there's nothing we have not seen before. Is that clear or not?
Yes.
Okay. Now let me look at derivative of g. what is g prime of x is minus 1 for x and minus 1, 1. Are we good here? What is h prime of x? H prime of x is the same as g prime of x. You agree or not? What is h prime of x? It's the derivative of pi over 2 minus arc sine. What's the derivative of arc sine? It's 1 over square root of 1 minus x squared. So h prime of x is also minus the square root of 1 minus x squared, as x belongs to, for x belonging to minus 1, 1. Okay, what can I say about the derivative of these two things on the open interval minus 1, 1? They're the same. So what can I say about the difference of these two functions? How do they differ? By a constant. You agree or not?
Yes.
The difference of these two functions have the same derivative on the open interval. So they have they're differed by a constant on this open interval. Hence, h prime of x is equal to g prime of x on minus 1, 1. So h of x is equal to g of x plus k on minus 1, 1, where k is a constant. Okay, are we good here? Now, I don't want you to think about theorems. I want you to think about velocities. Let's think about this in velocities. So, two people are walking at the same speed. Okay? The idea, what should this constant be? This constant should be 0. You agree with this or not?
Yes.
Guys, look at the question. This constant should be 0. So h of x is equal to g of x plus k. Well, okay, this is g of x, and this is h of x. Well, g of x plus k is equal to h of x. K should be equal to what? 0. You see that? That's what we're getting at. Now, if there are two walking at the same velocity, how do I make sure that the distance is the same? That they have the same position at every single time. So if I'm walking, we're at the same velocity, right?
Yes.
Do we have the same position? The chalk and I, do we have the same position, or does it differ by a constant? Differs by a constant. So how do we ensure that this constant is 0? If we have the same starting point and walking at the same velocity, do we have the same position? Same starting point, and we have the same velocity.
Yes.
Are we at the same position at
Yes.
any time?
Yes.
Think?
Yes.
Yeah? Everybody. If we're walking at the same velocity and have the same starting point, do we have the same position? Great. So what do I have to show here? I just have to show that they have the same starting point, that h and g have the same starting point. Okay, I'll erase this one here. Now this is where continuity is important. Okay, continuity on the interval minus 1, 1. What is h of 0? H of 0 is equal to what? What is h of x? H of x is equal to pi over 2 minus sine x. H of 0 is pi over 2 minus sine inverse of 0, which is pi over 2. G of 0 is equal to what? To cos inverse of 0, which is pi over 2. So both of these functions start at pi over 2. And they have equal derivatives. Yes? Oh, my sine of 0 is?
Oh, never mind.
Yeah. Okay, I mean, we could also put minus 1. What do you guys want? -1 or 0? Let's put this. Well, plug in x equal pi over 2. What do you get there? What do you get there? So I plug in h equals, so h of 0 is equal to g of 0 plus k. Now, what is h of 0? H of 0 is pi over 2. And g of 0 is pi over 2 plus k. So k is equal to 0. Hence, h of x is equal to g of x on -1, 1. Now here we have the closed interval. Okay? We need equality on the closed interval. There are two ways to proceed. Either plug in the values and check they're equal at 1 and -1, or you can just do a continuity argument. H and G are continuous on the whole interval, and they're equal on the open interval. So they must be equal at the boundaries. Okay? So since H and G on -1, 1, then h of x is equal to g of x on -1, 1. So sine inverse of x. Oh, well, what is h of x here? Pi over 2 minus sine inverse of x is equal to cos inverse of x for x and -1. Very, very good. These are very good. All of the mean value theorem questions are very good exam questions. So you could easily get them. Yes, sir.
When we're checking for if we're saying to start, why don't we use -1?
You could. I just picked up one in the middle because it's easier. Okay. Technically, the displacement, you know the displacement between the chalk and I is constant. Okay, we're working at the same speed. If at one point in the middle, you know that this displacement, the difference between the distance is 0, what does it mean? It means that we have already started. Okay? Think of it in terms of velocities. Great. Now let's do one more. Should we do one more? Shall we do one more like this? Let's do one more like this. I've written it. So it's arc sine of tan h of x show that for all x arc sine of hyperbolic tangent of x is equal to arc tan, or let's not use, I like sine inverse. Well, I like both, but let's use sine inverse. Is equal to tan inverse of sine, the hyperbolic sine of x. Okay, great. So really, I have to show that these two functions are the same. What's the first step? I show that the derivatives are the same on the whole real line, right? And then find a point at which these two functions are equal. And that does it. You guys see this? Yeah? Okay. So, how do we start? Let g of x. Okay, so all of these two lectures are very important. So please. So let g of x be sine inverse of tan hx, and h of x be tan inverse. Okay, for all of these you may not need this. You can just do this by trick, but we're just using this. Okay. Great. Now what do you have to show? We have to show that g prime. I'm afraid of differentiating this, but you know, let's see. No, I don't think that's bad. For x and r. Okay, so g and h are differentiable on r. You agree? Are differentiable on r. And what is g prime of x? G prime of x is sine inverse of tan hx. So what's the root of sine inverse? Is this 1 over the square root of 1 minus t squared times the root of tan h of x. What's the root of tan h of x? Is the hyperbolic secant of x. Now notice, what is the square root of 1 minus, what is 1 minus tan h squared? You have that cosh squared minus sinh squared is equal to 1. Right? So divide by cosh squared, you get that 1 minus tan h squared is equal to secant squared. Secant, hyperbolic secant squared. Okay, you should know your inverse trig formula very well. Now notice that secant h squared is always positive. Right? It's 2 over e to the x plus e to the minus x. Secant h of x is always positive. So the square root of secant h squared is really secant h of x. So this is 1 over secant h of x. So this derivative is just the hyperbolic secant of x. Now, I have to take the derivative of h. Since, let's say, since sec hx is always positive. Okay, now I have to take the derivative of h. What is h prime of x? So what's the root of arctan? It's 1 over 1 plus t squared. So this is 1 over 1 plus sinh squared x times the derivative of sinh. What's the derivative of sinh? It's cosh, right?
Yes.
Cosh x. Oh, well, that was very nice, actually. What is 1 plus sinh squared? 1 plus sinh squared is cosh squared. So it's 1 over cosh squared x times cosh x. Oh, wait a minute. This is 1 over cosh x, which is equal to hyperbolic secant of x. So these two functions have the same derivative. So they must differ by a constant. Hence, g prime of x is equal to h prime of x for all x in R. Hence, g of x is equal to h of x plus k for all x in R. Now, what's a good number to plug in? Let's plug in 0. So, to find k, plug x equals 0. What do you get? You get sinh sine inverse of tan h of 0 is equal, let's write it here. Sine inverse of tan of 0 is equal to what? To tan inverse of sinh of 0 plus k. Now, sine inverse of tan h 0. The acronic tangent of 0 is 0, right? It's sinh of 0 over cosh of 0. This is 0. So the sine inverse of 0. Sinh of 0 is also 0. So tan inverse of 0 plus k. Now what's sine inverse of 0? This is 0. Tan inverse of 0 is also 0 plus k. So k is equal to 0. Hence, f of x is equal to g of x, or h of x, for all x in R. Okay, this ends the series on mean value theorem. Please study this. Those two lectures are very important. Rolls. So we have seen. Maybe we can give a small summary. We have seen like three major results. Rolls theorem that help us bound the number of roots. How many roots does a function have? Then you have the mean value theorem using to prove inequalities, and then you have this theorem. Okay, that tells you if two derivatives, if the derivative of two functions are equal on an open interval, then these functions differ by a constant on this open interval. Okay, so these are the three most important concepts. Please practice them. Okay, thank you very much.